took Mangalyaan 9 months to travel from Earth to Mars, but now that distance can be covered in just 100 days. Sounds impossible, right? But NASA scientists have made this unbelievable thing believable for the first time. Currently, NASA is working on 2 nuclear-powered rockets whose speed and power are 5 times greater than SpaceX's Falcon rockets, which are among the world's most advanced. This means that while it used to take over 10 years to travel from Earth to Pluto, we can now cover that distance in just 4 years. But is it really possible to make this technology operational today? Because, as you know, in space travel, it's better to be late than to have an accident. If yes, how is NASA achieving such high speeds? Over the past 100 years, our ideas about space travel have changed significantly. In 1657, people thought rockets could be propelled into space using fireworks. This idea wasn't entirely bad because energy can indeed be created by burning liquid or solid fuel. In fact, when the first rocket, Bumper Whack, was built, it was successfully launched based on this idea. That was the moment the journey of rocket building began. Today, building rockets has become, comparatively much easier. The Indian Space Agency, Agnikul Cosmos, has even created the world's first 3D printed rocket, which has already been successfully tested. By the end of December, another 3D printed reusable rocket is set to be launched. In fact, the most powerful rocket we have today is still a chemical combustion rocket. Using these, Elon Musk plans to settle humans on Mars in the coming years. Basically, this technology is widely used and honestly, quite successful today. In this process, a controlled and continuous explosion is created in the engine, which helps launch rockets into space. The only difference is that space engineers have upgraded this method to generate more energy from chemical combustion and increase its efficiency. Today, improving a rocket's efficiency is a crucial part of rocket science. The term rocket science has a bad reputation because people think it's extremely complicated, but in reality, it's quite simple to understand. At its core, it uses Newton's third law of motion. Every action has an equal and opposite reaction. In chemical engines, liquid methane and oxygen are used as fuel. The resulting heat is expelled through a cone-shaped nozzle at the bottom of the rocket. The nozzle's shape is specifically designed to concentrate maximum energy in a single direction. Then, Newton's third law comes into play. The energy expelled downward pushes the rocket upward, and this force is called thrust. The more thrust a rocket engine produces, the faster the rocket ascends. That's it. That's the basic rocket science people call complicated. Of course, advanced rockets involve much more sophisticated engineering, but that's another story. NASA's main goal is to send humans back to the moon by 2025, and preparations are in full swing. But here's the major problem. We've been using chemical combustion technology for centuries, and it has significant limitations. Creating energy by burning liquid fuel is a highly inefficient process. Believe it or not, we can convert less than 1/3 of the fuel into energy. Manufacturing chemical rockets is also very expensive. For example, launching a small half-kilogram satellite into space costs around 8.28 lakh rupees, with most of the expense going toward fuel. Another major limitation is that space travel with chemical engines is very slow and time-consuming. Even with the best rocket today, Falcon Heavy, it takes about 7 months to reach Mars. This means astronauts have to spend that time in a low-gravity environment. The record for staying in low gravity the longest is held by Russian cosmonaut Valery Polyakov, who spent 438 days, 15 months, in space out of necessity. This caused his bones and muscles to weaken so much that it took him 8 months to readjust to Earth's gravity after returning. So, if we send astronauts to Mars using chemical engines, their first step on Mars might be in a wheelchair, leaving wheel prints instead of footprints. To avoid these consequences, NASA has a brilliant solution. In collaboration with the Department of Energy, or DOE, NASA is designing nuclear-powered rocket engines. They have two types of nuclear rocket designs ready: the nuclear thermal rocket engine and the nuclear electric rocket engine. A nuclear thermal rocket engine isn't much different from a chemical engine but can produce energy twice as efficiently. Here's how it works. A nuclear reaction generates a massive amount of heat, and when liquid hydrogen is passed through the reactor, it turns into gas due to the heat and is expelled at high speed through the rocket's nozzle. You might say normal rockets do this too, so what's the difference? Let's understand it with a simple equation. Engineers measure a rocket's efficiency using something called specific impulse, which is thrust force divided by fuel flow rate. The faster the fuel exits the nozzle, the higher the specific impulse, meaning higher efficiency. In normal combustion engines, fuel exits at 4 kilometers per second, which is fast, but in a nuclear thermal rocket, hydrogen exits at 8 kilometers per second, twice as fast, hence its efficiency is also twice as high. The second design is the nuclear electric engine. Here nuclear energy is used to generate electricity first instead of a controlled explosion. This electricity ionizes xenon atoms from the periodic table, which are then expelled through the nozzle to generate acceleration. And here's the kicker: the xenon exits at 40 kilometers per second, 5 times faster than nuclear thermal rockets, making its efficiency 5 times greater. That's why NASA scientists say we can reach Mars in just 100 days using nuclear electric engines and even travel from Earth to Pluto in 4 years. 4 years might sound like a lot, but remember, it took the New Horizons spacecraft 10 years to cover the same distance and send us the first HD photos of Pluto. Many of NASA's satellites already use electric ion engines. So why the delay in using this for Mars or other planets? The concept is simple, but executing it isn't. To increase efficiency, fuel velocity needs to be high, but thrust depends on the quantity of fuel expelled. In ion engines, the xenon fuel has high speed but very low quantity, so an ion engine rocket can't lift off from Earth. So it can only work effectively once the rocket is actually in space. Another issue is that nuclear engines use highly radioactive uranium isotopes, which are, honestly, pretty risky to handle on Earth. And if an accident happens in space, radioactive uranium could severely harm astronauts. In fact, the Russian space agency Roscosmos scrapped plans to use nuclear energy in rockets because of these risks, and the United States has restricted nuclear fuel use in space engines for the very same reason. Until NASA makes nuclear energy generation completely safe, they can't equip every spacecraft with nuclear engines. Still, NASA has found a workaround for this, but one problem remains: astronauts will still have to spend 100 days in low gravity. I know, generating artificial gravity by rotating the spaceship is a common method. This creates a centripetal force that keeps astronauts grounded. Many movies show this idea, but I'm not talking about that here. After all, gravity is just a form of acceleration, right? So, if we accelerate the rocket at a constant 9.8 meters per second, we can generate Earth-like gravity inside the spaceship. Now tell me, if space travel with nuclear-powered rockets becomes this easy, what other implications could it have? Write your answers in the comment section below.